Hello, today we are going to start a new topic called as Laplace Transform. So, what is meant by Laplace Transform? So, let's define it. So, let f of t be function defined for all positive values of t. Then, f of s is equals to integral 0 to infinity e raised to minus st f of t dt, provided the integrals exist, is called as Laplace transform of f of t, and it is denoted by L f of t is equals to f of s, which is equals to integral 0 to infinity e raised to minus st f of t dt. Okay, so you just have to remember this expression. Now, the important formulas which we will require while solving problems. Now, I have given these formulas, and in the next pages I have given proofs for these formulas also. So, let's see. Formula number 1 says L of 1 is equals to 1 upon S. Okay, so L of e raised to at is equals to 1 upon s minus a, where s is greater than e. Okay, let's do the proof for this first. As I said first, L of 1 is equals to 1 upon s. So proof, L of 1 is equals to integral 0 to infinity 1 e raised to minus st dt. So integrating this thing, what we are getting is e raised to minus st divided by minus s, 0 to infinity. So what we will get it here is minus 1 upon s comes out, 1 upon e raised to st, 0 to infinity. Else we are getting 1 upon s, 0 minus 1, which is equals to 1 upon s. Hence, what we have to prove? L of 1 is equals to 1 upon s. So, we have given a proof for, that is L of 1 is equals to 1 upon s. Second was L a of a e raised to at is equals to 1 upon s minus a, where s is greater than a. So, L of e raised to at is equals to, again same formula, integral 0 to infinity e raised to minus at. So it's having something e raised to at dt. So what we will do, this is minus s a. So this comes out to be minus s plus a. See this next step, 0 to infinity e raised to minus st plus at dt. So t comes out to be common, 0 to infinity e raised to minus s plus a bracket t dt. So what we are doing is, we are taking minuses common from this bracket. So it comes out to be 0 to infinity e raised to minus s minus a t dt. Else, after integrating this, e raised to minus s minus a t divided by minus s minus a 0 to infinity within the limits, which is equals to minus 1 upon s minus a in the bracket 1 divided by e raised to s minus a within the limit 0 to infinity. So as a result, what we are getting, this term will be there and rest will be 0 minus 1, which is equals to 1 divided by s minus a. Therefore, so what we are getting it here is L e raised to at is equals to 1 upon s minus a. So hence proof. So what we have to prove here is L of e raised to at is equals to 1 upon s minus a. So as mentioned here, so we have completed with the second formula. Third formula, what we have to prove is L of t raised to n is equals to n factorial divided by s of n plus 1, where n is equals to 0, 1 plus 2 plus 3. Plus 3. So your third proof is L of T of n is equals to n factorial upon S of S plus n plus 1, where n and s are positive. So L of T of n is equals to integral 0 to infinity e raised to minus of S of t, t of n dt. So we will put S of t, st is equals to x, and t is what? X by s. Dt will be ds by s. So L of T of n is equals to integral 0 to infinity e raised to minus x and then bracket x by s raised to n dx by s. So next step, L of T of n is equals to 1 upon s of n plus 1 integral 0 to infinity e raised to minus x of n dx. So L of T of n is equals to factorial n plus 1 divided by s of n plus 1, where n plus 1 is equals to integral 0 to infinity e raised to minus x and x raised to n dx, or this one n plus 1 factorial is equals to n factorial. So L of T of n is equals to n factorial divided by s plus 1 factorial. Rest 4 formulas will continue in the next lecture. Thanks for watching.